Alright. So in the last session we were discussing about DC-DC converters, DC-DC converters, converters. So here the important observation is that we are converting DC voltage to DC. There is no change in the nature of the voltage, but so there is a change in the level of the voltage, like from higher level to lower level or lower level to higher levels. So we were discussing about the like step down converter, step down converter, step down converter, step down converter, which is usually called as a buck converter, buck converter, buck converter. So in buck converter, so we usually have these things, like let me draw the things as like this. So we will have the input, which is voltage source, let us say Vi, and we will have the load where the output will be taken. So this is some load. Usually across the load we will connect a capacitor to smooth out the output voltage. If there are any variations in the voltage appearing across the load, that will be smoothed out. And this combination we see regularly, the load in parallel with the capacitor, and voltage across this load we will call as output voltage, which is V0. Now in between these, like the output and the input, we will have some mechanism. So that mechanism, what we call as buck converter. So where the buck converter, or let me use this with a different color, that portion of the system. So here we will have one switch. Usually this is high frequency switch. That means we can switch on and off this at very high rate, like for per second we may switch on this in terms of hundreds or thousands also. Such a fast switching operation can be done with this kind of switches. And we will have one diode as like this, and we will have one inductor. So this green color segment of the system, what it constitute, the converter, which we call as a buck converter, buck converter. And let me finish these connections completely as like this. And this is the inductor, and this is the switch, this is the diode. And here we seen in the last session, like the timing situation, timing diagram as like this. So if this is the time axis t, this is the 0, the switch may be closed for certain duration, which we call as on time. So this is what the t on time, and for remaining duration it will be off. This we call as a off time. So t on time plus t off time we will call the total time period. Then after this, again same kind of situation will repeat that. So again on time for certain interval, then off time, like this. It is continuously on off kind of situation can be done with the help of this switch. And here yesterday I was discussing that, so we can define the duty cycle or duty ratio, which is usually represented by the letter capital D, where capital D is the ratio between on time to total time period T, on time to total time period T. And here we can also express this on time T on in terms of the duty ratio as T on is equal to capital D duty ratio into total time period. So this we may see sometime, so depends on the numerical problems. And we can also express these things in little bit in different ways, like this. Can we write capital T as T on plus T off? The total time period is equal to on time duration plus off time duration. So let me write here, this is what the switching instances, switching instances, that when the switch will be on, when the switch will be off, that one. Okay. So now here can I write this T on as capital T, total time period, minus T off. Then if I'll substitute this T on in terms of the T off, so I'll get the duty ratio, I had written ratio on, so it is ratio, duty ratio is equal to, so T minus T off by capital T. So you can see this I can write 1 minus T off divided by capital T. Now from this we can also write T off, just to simplify this, so see that what you will get. T off is equal to 1 minus D into T. So D into T is what the on time period. In case if duty cycle is given, we can find what will be the on time, what will be the off time, provided that total time period is known. Okay. Right. So now with this, so let us see that during the on time what is going to be happen, during the off time what is going to be happen, that we seen. So just quickly let me take up those situations again, so for better understanding of these converters. So let me take, this is one diagram and one more diagram beside this. So now just I would like to take two cases, that when switch is on, when the switch is on, this is going to be closed. So then see that voltage across the diode will be in the positive upper side, lower side negative, which is Vi. So as because of this, diode will be in reverse bias, so this diode will be in off state. Off means it is equivalent to open circuit. That means I can remove this. It is like this, something like this. Okay. So then voltage across the inductor is VL. So let me write during the on time. So to avoid the confusion, VL on is this much voltage, and this is what the output voltage. This is what the case 1. This is what the case 2. So case 1 is, so during the on time, when switch is in on position. So we said simple KVL will make us simplified of these equations, minus Vi plus VL during the on plus V naught is equal to 0. So we can see that V naught is equal to Vi minus VL during the on time. So one thing you can observe clearly, that here when the switch is on, try to see how the current is flowing through this. This is what the current which is flowing through this system, and it going to be splitted as IC and IL or I naught. This is what I naught output current, this is what IC capacitor current. If you want little bit more analysis, you can go with the KCL at this node. I is equal to, or IL, you can say IL, inductor current is equal to, so capacitor current plus load current, which is output current I naught. So if you see generalized thing, that during the switch on position, the inductor is charging. So next is when it is in the off state, when the switch is in the off state, means it is open. Now diode going to be conduct, then this going to be short. Diode is in on state. Now diode is in on state, switch is in off state. So now see that voltage across the inductor. Now let me write as it is same polarity, but now it is in off state, VL off. How much will be this off state voltage of the inductor? Now in this duration, what is going to be happen? These things you need to analyze. This is what the inductor current IL, this is what the capacitor current IC, this is what the output current I naught. Now try to observe, as I told you in the last session, that inductor current does not change instantaneously. So current need to flow in the same direction as like just before the switch off operation. Here it is during the switch on how the current is flowing from left to right. Here also it should flow left to right. If it is flowing left to right, then still inductor need to charge. But who is providing that energy to charge this inductor? Nobody is there to drive up this inductor further charging, so it will not charge further. So what will happen is that so far whatever it was charged, that going to be supplied to the load. So in order to supply the power by this inductor to the load, then we need to make some change. That change is either current should be reversed or voltage should be reversed. As because by the property of the inductor, we cannot reverse the current. Why? Because current does not change suddenly in an inductor. So voltage can change across this inductor. That means polarity will become this side plus, wherever left side minus. Then now see, positive current is entering at the negative terminal, then it try to supply the energy which was stored in the previous cycle. So now during this situation we can write as either in either of the forms as like this. So VL of plus V naught is equal to 0 KVL. So VL of how much we will get is minus V naught. Minus V naught. Now one more interesting point which is usually whenever we talk about these converters, which is usually come across is that the output voltage, average output voltage. How much will be the average output voltage? We seen average values, RMS values. Usually these are evaluated over a complete cycle. Like during the on time, how much will be the voltage? During the off time, how much will be the voltage? Average of those two adding up will give the total time period average value. Let us see that how much will be. So in order to get that, we will use one more generalized universally known principle that for the inductor, let me write this statement for inductor, so volt second, volt second balance, volt second balance, uh, volt second or how should I say is that for inductor, the volt second will be balanced. Volt second ratio things will be balanced. I'll show what is volt second means. Just let me assume that this is the situation that during the on, the inductor is charging. During the off time, the inductor is supplying the energy which was stored in the on position. That means, so the amount of the energy stored on the inductor must be supplied to the load during the off time. So in this way, you can see that inductor will neither generates the energy nor destroy the energy. The amount of the energy which was picked up during the on state is equal to the amount of the energy which is supplied to the load during the off state. That is what the volt second balance. Volt second balance for the inductor. So is that, so the amount of the energy pickup during the on time is equal to amount of the energy supplied to the load during the off time. That's it. So this is for ideal inductor. And what is volt second is that if you remember this expression, voltage across the inductor is equal to L into DIL by dt. Then if you see this, VL into dt is equal to L into DIL. L into DIL. So this is what the volt second balance. So see here, voltage into time. So generally for inductor, volt second balance must be balanced in such a way that during the on time voltage into time is equal to during the off time voltage into time. So that nature must be balanced for the inductor. So voltage units are volt, time units are seconds. So now just let us see this during the on time, how much will be the output voltage? How much will be the output voltage? Or yeah, so or you can even take let me write the inductor voltage here also, so that instead of in the output voltage, so I can write this in VL on is equal to, how much is that? Vi minus V0, Vi minus V0, and here also VL off is there. Now what I'll say is that in this way, VL on as per this volt second balanced equation into time T on is voltage into time, means during on state how much is the voltage across the inductor into its corresponding interval of time is equal to voltage during the off state into the time interval during the off state. So now let us substitute these things. So we will get the interesting thing that, so Vi minus V0 is equal to into T on is equal to V of is minus V0 into T off. And see that, try to make this to be simplified and just try to get it, how much will be the output voltage. So can I write this as Vi into T on? I'll bring either side, this right side term to left side. So what I'll get, let us see that. So this become minus V0 into T on and plus V0 into T off. So is equal to 0. Then let us see whether I'll get properly or not. I think here I made volt second balance. Yeah, so I made small mistake that this output voltage volt second balance, I should look in this way, that during the positive half cycle and during the negative half cycle. So this negative sign will not be there. So, or you can write this as in this way, minus is equal to 0. So on state corresponding thing, off state minus off state corresponding thing, that the energy during the on state is equal to energy during the off state usually. So that will satisfy this. So what I'll do is that you can take this same thing, but let me take as a minus plus, then yeah, is this satisfying? Yes. This become minus, then this should be plus volt second during the on state plus volt second during the off state together is equal to 0. Now it satisfies. Check it. So volt second during the on time, volt second during the off time must be 0. That is what the volt second balance. So during the off time, how much is the VL off is minus V0 into T off is equal to 0. Now it will give you the proper result, that this is minus V0 into T off, this is T on. Then if you simplify this, just try to see this, V0 is equal to Vi into T on divided by T on plus T off. What is T on by T on plus T off? So T on divided by T on plus T off is D, duty ratio. So usually for a buck converter, we will get the output voltage is equal to duty ratio times the input voltage. Duty ratio times the input voltage, where D will be between 0 to 1. 0 to 1. It will not be higher than this. So the output voltage will never exceed the input voltage. So output voltage is lesser than the input. That's why it is called as a buck converter. Okay, step down converter. Right. So in the same way, let us see the another important converter, which is boost converter. Boost converter. Just let me give you one simple problem in understanding these converters in a more effective way. So just let me take one problem, right? So here let us consider a DC-DC converter, DC-DC buck converter, has some of the following things as like this: input voltage is equal to 50 volts, inductor L is equal to 400 microhenry, and capacitor C is equal to 100 microfarad, and frequency, switching frequency usually 20 kilohertz, 20 kilohertz, and uh, any other things are there? That's all. So inductor, capacitor, switching frequency, and the load will be given as load resistance RL is equal to 20 ohms. 20 ohms. Now for A, if duty ratio is equal to 0.4, and for B, if duty ratio is equal to 0.8, find V naught. How much is the output voltage? So what we need to do here is that first, so we need to see everything is given straight away, so no much difficult things are there. So the output voltage is equal to, for a buck converter, duty ratio times the input voltage, straight away directly. So you can write for A bit, V naught is equal to 0.4 into 50. For B bit, V naught is equal to 0.8 times of 50. So how much is these values? Just calculate and tell me. 0.4 into 50, 20 volts output voltage, and 0.8 into 50 is 40 volts. Okay. Right. So now let us move to the next converter, which is the boost converter or step up converter, boost converter. It can also be called as step up converter. And see, as like in the previous case, we will have the input is a voltage source Vi, and the output is a load. Across the load we will have capacitor. This is the usual thing for any type of converter. This is the capacitor, and then so these are connected, and now it is connected with some system as like in the buck converter. In between these, this is C, this is the load, and current is IC, load current is I0, and this is the source. Okay. So now what we do is that, just unlike the buck converter, here slight same components. So switch will be there, diode will be there, and inductor will be there. So these converters mostly played like turning those things in some clockwise, anti-clockwise, like that. So previously what I have is that like this, one switch was there, let me put over here, and one diode was there, one diode is in this way, and one inductor was there as like this. Okay. So like a T junction, T. So if you turn this T by, let us say, 180 degrees, 180 or yeah, So somehow if I'll turn these things in counterclockwise direction, inductor will occupy the switch position and switch will occupy the diode position and diode will occupy the inductor position. Such a position, the elements we need for the boost converter. Same thing. Generally, all DC-DC converters are played with these three elements. One is the switch, diode and inductor. So let us see how we will connect. Here we will have inductor and here we will have switch, that switch, and here we will have diode as like this. Now this red color highlighted portion is what? The boost converter. This is what the boost converter. We'll see. So how it this portion is what we call as boost converter. Boost converter. Now again same principle, that during the on time, off time, what will be the situations as like this. So let me take the case 1 and case 2. So then the, let us say case 1. So during the on time, when the switch is on, this is what the switch, so this is what the diode, this is what the inductor. Okay, so diode D, not duty ratio. Then if you want, let me not to represent this. So during the on time, what happens? So let me take this same diagram. And see that, just I will try to take side by side so that it will be very much helpful. And during the on time and off time, we will analyze both the circuits. Okay, so let us see that. So case 2 is during the off time, when T off period. So now let us see, if the switch is on, what happens? If this switch is on, this switch going to be closed. Then as a result of this, see that, so what happens is that, so voltage across the inductor will be equal to the input voltage Vi. This is the inductor. Input voltage Vi is equal to VL, and here output voltage is V0. That output voltage is appeared across the diode as with this polarity. See, this negative polarity will come over here as it is, and this positive is in this way. So thereby diode is in reverse bias. If it is in reverse bias, what happens? It's going to be in off state. So during on time, inductor is directly connected across the source, thereby inductor going to charge. This is what the inductor current. Inductor is charging. That means current is rising with certain slope. How much is that slope? You can express that with the help of equation. I'll show that also. So this is what the during on state. What is happening is that inductor is gaining the energy from whom? From the source. Then after that, during the off time, this switch will be off. Means, so it is in off state, open state. Now see that, so the voltage across the inductor, diode, now the voltage across the diode will be this one, which is V 1 or V some 2, anything. Instead of D, so I am using some different suffix. Now see that what happens is that, just till the previous time instant, that is up to T off instant, current through the inductor was IL. So as I told you, current does not change through the inductor suddenly. So the moment you switch off this, the voltage across the inductor, its polarity going to be changed. This become plus, this become minus. Now with the help of this, you can see that voltage across the diode V1 will become as Vi plus VL of Means during the off state voltage. During the off state voltage. If you want, yeah, no issue. So we can take in the same way. So, or let me off state voltage. Anyhow, no issue. Off state voltage. Uh, this is what V1 minus V0 minus V0. This is what the output voltage. Just I am writing simple KVL equation, but just I wrote directly. See that now voltage across the diode will be positive and the diode going to be in forward direction. So thereby this is going to be on. Just I am writing directly. This is in on state. Which one? Diode. Here diode is in off state. Now see what happens is that whatever energy stored by the inductor so far plus additionally input voltage Vi will try to supply the power to this load during the off time period. Now for these two intervals, just let me get what will be the inductor voltage. So inductor voltage VL, this is what the VL, and here also let me put same polarity or it's your wish. So let me proceed in this way. VL on is equal to Vi. It is straight away, just I am not even writing KVL, like minus Vi plus VL is equal to 0. Okay. So this is what during the on state. What about during the off state? During the off state, you can see that minus Vi. So the actual voltage across this will be positive on the left side, negative on the right side, as like case 1. So which I will take as a reference VL of, so plus VL of plus V0 is equal to 0. Okay. So let me remove this equation, it is of no use. So now how much is the voltage across the inductor during the off state with respect to blue color polarity, blue color indication which I given over here. The actual voltage may be reverse, but here whatever voltage I had taken reference is on state reference I am carrying forward. So I am using the blue color polarity, left side positive, right side negative. That kind of convention I am adapting. So this is VL is equal to VI minus V0. Vi minus V0, and which is usually equal to negative of V0 minus Vi. V0 minus Vi. You can write in either way. Now again, as like in the buck converter, let us proceed here in seeing the volt second balance of the inductor. Volt second balance of inductor. This must be satisfied. What is that? So voltage during the on state into on state time interval plus voltage during the off state into off state time interval is equal to 0. Now let us see what we will get if we do these things. So this is Vi into T on plus, so VL off is, so you can write this as minus V0 minus Vi, or plus directly you can write, no issue. So Vi minus V0 in either way, no issue, into T off is equal to 0. And see that what can we do here? So if I'll take Vi common, I'll get to T on plus T off here in the first term, and is equal to, I can write this as V0 into T off. Now just further simplify these things. So we will get some interesting thing. So V naught is equal to what we get? So Vi into time period capital T. Why? Because T on plus T off can be written as T divided by T off. T off. So this can be written further as Vi into T can be written in terms of T off as what we do is that can we do something for this? Or so if I'll keep same thing as it is, T on T off, what I'll get is that, just to let me try whether I'll get proper or not. T on plus T off by T off is equal to what we get is 1 plus T on by T off, T on by T off, and 1 plus T on means D into capital T. T off means 1 minus D into capital T. So what I will get is that, just let me check, 1 minus D plus D by 1 minus D. Yes, yeah, fine, no issue. So we can even directly write here also, I think. So we can write here also directly as like this. So capital T divided by T of we already derived here. See, T of in terms of where this one, somewhere I had written 1 minus D into T. So I can write that as 1 minus D into T. So which is equal to 1 by 1 minus D into Vi. This is what the output voltage, and this D will be 0 is less than D is less than 1. It will be in between 0 to 1. That means denominator will be lesser than 1. Anything which will be lesser than 1 in the denominator will be the higher voltage than the Vi. See that V naught is greater than Vi from this expression. That means it is step up converter. Step up converter. Step up converter. So up to this is some important concept, like just if you want I can give you the time diagram also as like this. This is T, and let us say that during the on state what is going to be happen, during the off state what is going to be happen, and let me extend this for at least 2 time interval. This is capital T, this is T on, this is T off. T on also equal to capital D into T. T off is 1 minus capital D into T. What is the D is duty ratio. Now, so let me extend this, that. So, T, and during the on time, let me take these things like this. Some intervals like during what time interval it is on, off, etc. So try to observe these kind of things going to take place. That so during the on time, the inductor is charging from minimum value to maximum value like this. And let me take tick value. The inductor current is rising like this. This is what the inductor current, IL, inductor current. Then once the switch is in off state, immediately current going to be fall down. Again once it is on, again it will rise. Then further it will fall down like this. So rising means charging, discharging, charging, discharging. This kind of nature going to take place for the inductor. And when it is charging, what will be the volt second balance? Then when it is discharging, what will be the volt second balance? Those must be satisfied. Okay. So you can work on those things. So if you will work on those volt second balance for the inductor, you will get the output voltage is equal to input voltage divided by 1 minus D. So just let us have one problem on this also, so you will get a better understanding. Let me take the problem as like this. So a step up converter, a step up converter, step up, it can also be called as boost converter, basically boost converter, or these usually called as chopper also. Generally these DC DC converters, let me write here, DC DC converter can also be named as chopper. Other name of these converters is chopper. Chopper is which is chopping the current, like on off, like so zero current and on current, some current like that. So that's why these names came. So DC DC converter is also called as a chopper. That may be chopper means it may be buck converter, or it may be boost converter. If it is a step up chopper, it is a boost converter. Okay, right. So a step up chopper or boost converter is used to feed is used to feed is used to feed a load a load a load a load at 400 volts DC, at 400 volts DC from 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 a 250 volts DC source. So the inductor current is continuous. This is the assumption. The inductor current is continuous. Inductor current is continuous. Next is if if the of time of the switch is 20 microsecond. So what will be the what will be the what will be the switching frequency? Switching frequency. What will be the switching frequency of the converter? So just let me give you that switching frequency. You all know that. So the frequency is what? The reciprocal of the time period. That means once I know the time period capital T, I can say reciprocal of that is what? The frequency. So as because it is on and off things, so which is the switching action, so we call this frequency as switching frequency. So how can we get these frequencies? By finding the time. How can we find the total time? By getting the on time period and off time period. Okay. So let us see how we will find these things. Right. So here, what are the things given? Just check it. It is a step up converter. As they said, see 400 volts is on the load side, which is output voltage, and input voltage is 250. Is the output greater than input or not? Check it. So let me write here V out is equal to 400, which is a DC volt, and V in is equal to 250. And for a boost converter, we already seen that output input voltage relation, that Vi divided by 1 minus D. Whereas for buck converter, output is equal to D into Vi. Okay, depends on the nature of the converter, you need to take the corresponding relationship. Okay, so from this we can find the duty ratio. So let us see how much is 1 minus D. 1 minus D is equal to Vi divided by V naught, which is equal to 250 divided by 400. How much is this? 250 divided by 400 is 25 divided by 40. How much is that? 25 divided by 40 is 0.625. This is what 1 minus d. How much is d then? D is equal to, so 1 minus 0.625. How much we will get? 0.625. 0.375 is what the duty ratio. But what is duty ratio exactly? It can be written as T on by capital T. This can also be written in other forms as like this. Duty ratio is equal to T on by capital T, which can be written as T on also can be written 1 minus, or let us say not 1 minus, it is T minus T off divided by T. Why I am taking this is the off time is given. See, the off time of the switch is given. So what I know is off time. So that we can make something out of this. So off time is given. So why I am writing T on as capital T minus T off is that we know that total time on plus off is equal to capital T. That's why I am writing T on as capital T minus T off over here. So from this, can I say 1 minus T off divided by capital T is equal to duty ratio. Now in this, I know D 0.375. I know T off, how much is the T off? 20 microsecond. So let me keep as it is in micro divided by capital T. Then how much I will get this? So 20 divided by capital T is equal to 1 minus D, which is 0.375. So 1 minus 0.375 is 0.625. So 0.625. So this is 20 by T. How much is the T? Total time period. 20 divided by 0.625. 20 divided by 0.625 is 32. What are the units? Microseconds. Now once you know the capital T, now switching frequency F is equal to 1 by T, which is equal to 1 by 32. So micro means it will become mega. So let us see how much we will get into 10 power minus 6 micro means. So how much is this value? 1 by 32. 1 divided by 32 is 0.03125 megahertz, or if you take 10 power 3, that becomes kilohertz. So I can write this as 31.25 kilohertz. You can verify whether it is correct or not. Okay. So in this way you can use these relationship, duty cycle and the input output relationship, to get many of the things. Sometimes things may be asked in this way also. So duty ratio will be given in terms of, let us say, like for the same problem, if I'll give, let me take second case, next case, case 2, or some general case, or next problem. For the above problem, for the above problem, for the above problem, if so, if what I'll say is that if let us say D T total T is there 32 microsecond. Yeah. So if T is equal to 32 microsecond, no change in this, but and let us see T on, how much I'll get is T on, that is T off is 20, so means 12 I'll get. So what I will do is that T on I will decrease. So 10 microseconds. 10 microseconds. That means how much is the T off? So if this is the information, so for the given, for the given, Vi is equal to 250 volts. Find V naught. Find V naught. So what we need to do? We need to find duty ratio, that's all, and we need to use the input output voltage relationship. So for which you can see here, so directly D is equal to T on divided by T, which is equal to 10 divided by 32. This is what the duty ratio. Then V naught is equal to input voltage divided by 1 minus D. Then if V naught is 250, so see 250 divided by, so 1 minus D is, so 1 minus 10 by 32. So how much we will get? So this is 250 by 32 minus 10 is, so 22 divided by 32. So that becomes, so into 32.
363.6.
363.6 volts. Is that correct?
Yes.
See that just by decreasing the on time for the like switching operation. So for this switch, if I'll decrease 2 microsecond, usually previously how much is the T on is 12. What I did is that, so T on I decreased to 10, means I am switching on the things only 10 microseconds instead of 12. So output voltage is reduced from, how much is the output? It is 400, from 400 to 363 it reduced. That means if I reduce the on time, the output voltage will reduce. If this T on is 12, then you will get definitely this as 400 volts. Clear? So like that we can play among this relationship. Just you need to like have a better understanding on this relationship for the buck and boost converters. So based on that, problems will be framed. So output voltage, let me write, finally summarize that. For buck converter, for buck and for boost converter, for boost converter. So buck converter means step down, boost converter means step up. Okay, this converter can also be called as a chopper. That is one more important point. For both cases, so the duty ratio remains the same. That is T on divided by capital T. This can also be written in many forms. Duty ratio. T on can be written as T minus T off divided by capital T. That means 1 minus T off by capital T. So in either of the form you can write duty ratio. Okay. Here also same thing, or let me copy and paste. For the boost converter also you will see same kind of duty ratio relationship. D definition itself is the same for the buck and boost or all kind of DC-DC converters. No change in that. Next is the output voltage is equal to duty ratio times the input voltage for the buck converter, and where the D is definitely lesser than 1. So see that if T on is equal to capital T, then only it is 1. So otherwise in all other situations this will be lesser than 1. So 0 is less than capital T, or duty ratio capital D is less than 1. Whereas here V naught is equal to, so Vi divided by 1 minus D. And here also duty ratio will remain the same. 0 is less than, D is less than 1. So remember these are two important output voltage relationships for these buck and boost converters. Up to that much it is sufficient for you in understanding these converters at the block levels. I am not going much more analysis of these. It has a lot many things actually, but it is given in the syllabus that only block level analysis. That's why we are seeing only the generalized principle of operation, how it will be helpful for various applications. Like in, let us say you want to design some system, like some application in the project where, so you have 250 volts but you need 400 volts DC. Instead of just this kind of application, you have 250 volts DC but you need 400 volts DC. What you will do? Let us say some robotic applications is there. So where in lab we will have only 250, but your motor, some motor which try to provide some torque to rotate some arm of the robot, then you need the 400 volts DC motor. Then in that case you can go with this kind of segment of the converter between the input and output. This load means like some robo arm which we need to lift up and down. For that I need some motor. So here some motor is connected. In order to run that motor I need 400 volts, but I have only 250. What shall I do? I will design this boost converter in such a way that what will be the on time, what will be the off time, what will be the inductor value. If I'll get these parameters, then I can connect that kind of network over here between our required system with the input. Then I can achieve 400 volts. That is what the application, which is very important, especially for electronics students. Okay. So that's why try to see this buck and boost converter operation in generally, how does it works and what is the main motto behind these two converters. Main motto behind these two converters is that we are completely dealing the DC system in these converters. We have the requirement of stepping up the DC voltage or stepping down the DC voltage. So depends on such a requirement, we can go with either buck converter or boost converter. Buck converter will step down the DC voltage, whereas boost converter will step up the DC voltage. So here let me write, it is step down function. Step down, it will step down, this will step up, step up. So just try to remember these three important points about these converters. So with this let me conclude the session. So thank you all.